Recorded. Okay, so welcome to our second seminar at UNE, and we're very happy to have Professor Norman Dancer visit us and give a seminar. So this is very novel. We have a visitor, so that's good. And correct, I may get this wrong, but Norm was a professor here at UNE for 20 years, and 25 years ago he moved to Sydney. And now we're lucky enough to have him back, especially in this COVID era. And today Norm's going to talk about convergence to equilibrium for some competing species models with large interactions. So over to you, Norm.
Okay, it's a pleasure to be back here. It's I come back occasionally, but I always like coming back. Okay, to getting started. There's a general question here, which I just should mention. We don't have very good techniques for proving differential equation models that tend to a stationary solution as t tends to infinity. There's just not very good techniques. And we'd like to have more techniques to be able to do that. Now, I just want to talk about one example where we make some progress. But I think there is some general questions lying behind this to get better techniques. So the competing species models is simply where we have two components, U and V, which are two animals competing, or two various other things in the same region, and we're interested in the behaviour of these, and we're interested in particular what happens in the limit as t tends to infinity. So you can see the equations. It's u dots, by the way, is the partial derivative of u in t equals Laplace n of u plus f of u, which is the, and minus kuv is the interaction between the two u and v. And so the other equation is very similar. It's v dot equals d times Laplace n of v plus g of v minus the same term minus kuv. So in some, omega is a bounded open set, so we have these opening on omega cross R. We've got a boundary condition that u equals v equals 0 on the boundary. And we're assuming, because they're populations, that u and v are negative. And I'll always assume some technical conditions that the functions f and g are C1, they're concave, and f of 0 equals g of 0 equals 0. The diffusion coefficient in the second equation is positive, and we'll see it's d equals 1 and d does not equal 1 does make a difference. And then as ever, omega is a bounded open set with a reasonably smooth boundary. We don't really need too much smoothness. And if we're interested in the case, the intersection parameter k is large positive. So the two species are competing very strongly. There's another case you could handle quite well, is where the interaction is very small. By the way, I'll just mention in passing, there's another set of models. These are population models. There's another set of models which are very similar, and you can ask similar questions too, is where you have ku v squared in the first equation, ku squared v in the first equation, and ku v squared in the second equation. That's a similar model but behaves differently. So there's a lot of separate questions for that. The type of things you can answer for the two are slightly different. No, I said that's something to do. Yeah. Now,
sorry, Norm.
Yes.
When you mean k is large, do you mean k is order 1 or k is much bigger than 1?
I mean, the case I'm interested in is k is really large. It's a big number, so it's a very strong interaction. Okay. And yeah. No, I really mean, the theory probably it tends to work with extremely large k's. How large it is something you have to do using a computer to do. And to get I'm looking, in a sense, looking at the limit as k gets very large. And
right.
And the two cases you can, it's easy to make progress. If k is small positive, which is or K is very large positive. They're the two cases
Yep.
you can easily hope to do. The others, I think, are probably pretty hard.
Yep. Good. Yep. That's what I was wondering. Okay.
Now, as I said, this is really a very standard competing species model. I've just lost my track here. And as I said, what we would like to prove that both components have limits as t tends to infinity. Notice the assumptions I've made. It's easy to prove that u and v stay uniformly bounded. So that's not a problem. They don't blow up at all. And but we want to prove they have limits as t tends to infinity. Now, there's no obviously up on a function. And there's, in fact, as I said, there's a so which makes it hard. And there's actually lots of other models as well where we'd like to prove they have limits, where we don't have a Lyapunov function. The reason here we can do something is we've got a sort of limit problem which behaves well. Now, we need two technical assumptions, which probably can be weakened. And I need a condition which is, in a sense, almost a linear condition, but not quite. It's minus Laplace. If you think of d equals 1, for example, the first term is just minus Laplacian of w. And then the equation I have here is actually fairly standard. It's, but the general case is the one we need here, where we have minus Laplacian of w plus dw minus equals f naught w plus g prime naught w minus. Notice this is, and the usual boundary condition. Note this is a positive homogeneous, because if w is a solution, a positive multiple of w, a non-negative multiple of w is again a solution. So there's it's something that's linear-like but not linear. And we're assuming that our assumption is this equation has only the trivial solution. It's the case where d equals 1. This is quite a lot is understood about when this happens, and that's work of Fuchik, who did this a long time ago, and various other people have done various things on this. But that's the first condition we need. These are fairly technical conditions. And the second one, basically we need the second one to understand solutions where both components stay small. And the point being is that you've got a term f of u. If u is small, f of u is well approximated by f prime 0 times u plus little higher order terms. So this is really a limiting equation where we linearize the nonlinearity f of u and g of v near 0, and we get this limiting equation. So we need to assume that this problem has only trivial positive bounded solutions in omega cross R. Turns out a lot, these ones you can get, both of these, you can get quite a lot of conditions and these work, but I won't talk much about them. But you can do quite a lot on those. Those simplified equations, you can do quite a bit. And as I said, this one is real, the second one is really for understanding the solutions where both components are always small. And and in a sense, in some sense, this second one, it has the, if you take the difference, you get something that's looking more like a linear equation, as if you subtract, the UVs cancel out. So you've got something there which you can get some information on. But I don't want to discuss these two. Now, it turns out there's also a limit problem, which gives us a chance. The limit, I'll write it down, then say what it is. The limit problem is z dot equals Laplacian of z plus minus dz minus. By the way, z plus is the positive part of z, which I should have said earlier, and z minus is the negative part of z. Plus, then there's plus fz plus minus g minus z minus. And there's a mistake here. Z equals 0 on the boundary. It's z equals 0, not z minus 0. There's a typo somewhere on the line. Okay, now this equation is in fact is a limiting equation, which I'll explain in a minute. And if D, once again, if D equals 1, the first term of the first equation just becomes Laplacian of Z, which makes it somewhat easier. So if D equals 1, as we're going to continually find the case D equals 1 is easier. The other important part about this equation, which actually is vital to us, you can write down, which I'm not going to write down explicitly, an energy for this equation 4, and show that the energy of solutions decreases as T increases. And so this has the effect that the energy of this equation serves as a Lyapunov function for this equation. And so you can use this to prove that the solutions of this equation, and I want to write it out very formally, approach stationary solutions T tends to infinity. So this limit problem, I'll explain in a while why it's a limit problem, has nice properties for our purposes. So solutions of this limit problem actually approach stationary solutions as T goes to infinity. And by the way, there's an aside I should make here. In fact, D equals 1 or D does not equal 1 does make quite a difference in things here. But what is interesting, if you look at only stationary solutions, it doesn't make very much difference at all, because you can change variables to get something that if you change variables in this equation, you can make another variable, say is W equals Z plus minus DZ minus. If D equals 1, you can turn it into a more standard equation that's a heat operator with nonlinear terms. So the case D equals 1, the case where you would look at the state time independent solutions, the size of what D is doesn't matter nearly so much. And it's the main problems are going to be when D does not equal 1. Now, as I said, we can prove using energy that for this problem, the energy is an Lyapunov function. So this problem at least, and as I'll explain in a little while, is a limit problem, that the solutions of this do approach stationary solutions. And that's the key observation, in fact, of what we're going to do. Now, I think, did we miss something here? Just check. Three.
Just to finish.
No, sorry, I'm checking the things. That's right, yeah. Now, I want to talk here about two theorems. And the first one is a theorem with D equals 1, is that this is an old theorem. It's me with Zitao Zhang in Journal of Differential Equations in 2002. This was actually done when Zitao Zhang was a postdoc of mine in Sydney. So it's good. And this is saying if the case D equals 1, that under very general conditions, the solutions that are a problem for D equals 1, I stress, approach stationary solutions under those assumptions we have. And the stationary problem is the obvious one. You just drop the U dot and V dot, and you get, and I've just rearranged the terms, but it's the obvious stationary problem. And so this is the older theorem. Now come back. I want to say more about that. Okay. Now I want to, that's it. Just a comment on, I'll say more about the proofs. Maybe I will change it and leave that for the moment. There's a second theorem for general D, which is and this has been changed since I originally typed it, assume that any connected component S of the stationary solutions, and I wanted the, of this, which are the solutions of this equation, are smooth manifolds, or the small manifolds. Then you get the same conclusion as theorem 1. Now, there's a couple of comments here that, in fact, the solutions could be isolated points, isolated solutions, and that is counted as a C1 manifold. And in fact, you can improve C1 manifold to C0 manifold because it turns out that's good enough because you can use regularity. Now, as you can see, the original statement was slightly wrong. That's why it was changed. Now, a couple of comments here. That if in one space dimension, where this is already non-trivial, the connected components are automatically C1 manifolds. They're isolated points. So if n equals 1, there's no problem. And also, as I said, in general, if you know the points are isolated, you also know they're C1 manifolds if they're isolated, even in all dimensions. Now, it turns out, actually, I'll come back and talk about proofs in a little while. The proof of this is much more complicated because it depends on if it uses the manifolds in the following way. If you've got a manifold, you can find a nice neighborhood of a reasonably smooth manifold, which is called a tubular neighborhood, where you move out basically on the normals, a small distance on the along the normals to the set, and you get an expanded set, which is a C1 manifold. And
Norm, can I ask you a very quick question?
Yeah.
So you're talking about the solutions to the system here, which are a priori they're functions.
Yes.
When you talk about these manifolds, are you referring to level sets of these?
No, I think of these this equation is the solutions you might have, write an equation, you might have a number of solutions. There's a number of different W's. Generically, probably they're likely to be isolated. There's isolated solutions, but they're not always. They could, if you've got a symmetry, for example, you can have non-isolated solutions because you can use the symmetry acting on solutions to get another solution.
So are you talking about manifolds inside the function space, are you, in some sort of infinite?
Yes, they're manifolds in the function space.
Oh, I see.
Okay, so that's a fair comment. I should have made that clear. But as I said, you get a tubular neighborhood intuitively by looking at your manifold and go normally, and each point you would move out along the normal on both sides. And that way you expand get an expanded neighborhood of the original set in a rather nice way. But you can this only works basically if the set's a manifold. There's to get this nice construction, and you can control its topology.
Yes, that begs the question, Norm. What metric are you using in this function space to do these geometrical constructions?
Basically, it's the natural Banach. You've got a metric if we're working on a Banach space, it's usually something like maybe a space of bounded functions, where you've got a metric, a norm on a Banach space, and you use that as your from your metric. You've got a metric, a natural metric on. You might think of this. Sorry if you can't hear me. You might think of this as a not always the most convenient one. You could look at the space of bounded functions, and you can find you can define what's called the norm of a function by its sup of its absolute value. If you have a bounded function, you can take the sup of its absolute value, and then if you can get the distance between u and v is the norm of u minus v. Does that make sense?
Yep.
U. And that way, it turns out that's not the most exactly convenient metric, but there's slight variance of that, but you can get reasonable metrics on these spaces, which are metrics that fit in also with the linear structure. These metrics are, it's a metric that fits in both the metric structure and the translation invariance caused by the linear structure. So we're working on a space that's got both a linear structure and a metric structure. And that's typical what an awful lot of work and analysis uses. Yeah, sorry, get back there. Now, as I was saying, I think that you can get what why we can do things if these components are good is we can choose these nice neighborhoods, and that where we can do computations. Yeah, it's tubular neighborhoods very much in the sense of differential topology, but we need some smoothness here to be able to do the construction. How are we getting on? I'm going fairly fast. Yeah, no, that's going. I was just checking what I've done and what I haven't done. That's all. That's all. Now it turns out that we've got to work and estimate the u dot, by the way, is the time partial derivative of u, and we've got to estimate u dot and v dot quite well to be able to. We're trying to pass to the limits, which I'll explain in a little while. But and the reason for the difference is certainly it turns out if we stay away. There's some bad points here. I think of the there's a slide I'm missing here. On my fault, actually. I think. No, okay. There's the now the what we I was like, now I was leaving a little bit. Turns out we need to estimate, be able to estimate mod u dot plus mod v dot, and it's what happens is this is where's the major difference. The first, the case where k equals 1, the d equals 1. Sorry, d equals 1. If you look at those two equations for d equals 1, you can write if you take a subtraction, you get u dot minus v dot plus equals Laplacian of u minus Laplacian of v, or Laplacian of u minus v. So basically you're getting a term, the time partial derivative of u minus v plus the Laplacian of u minus v if d equals 1. So the two fits together well, and it turns out you can control the derivatives of these very well by the. You can see that these equations here I'm talking about in this equation 3 here. You can see that you get the terms. If d equals 1, it's all the first term on the left and the term on the right. Basically involve u minus v, and it turns out that makes them much easier to understand, and it's much easier to get bounds. And but you can get
the page.
Yeah, this last page. There's 2 pages to go actually. Yeah,
there's one.
I think it's somewhere along the line. The there's something else I somehow seem to miss lost is you can say for large K you can say something about the solutions, which is important, and I think that somehow the page has gone missing here somehow, which is not what I intended. And we come back to a limit problem. I want to say something about that, which I think I'm sorry, I somehow lost the page. Go back. Limit problem. Keep going. Yeah, now I just want to explain here something that's been missed. I said this limit problem came, you can get this limit problem. I didn't say, which is where a page has gone missing, if we're looking at large K, if the solutions are of moderate size, KUV is going to be, if the solutions are moderate size, go back to the start. This is important information. If you've got this term, if solutions are of moderate size, and you can prove the U and the V are uniformly bounded, if K is large, if everything is going to be of moderate size, it's reasonable to guess U times V is small. So in fact, what you get is a term, and then, if V is not, if V is not small, this term KVU, it's KV, which will then be large times U, is a big damping term, and that tends to push rapidly U down towards 0. So in the first equation, if U is not small, the large K forces U rapidly to 0, and it turns out even U dot rapidly to 0. And similarly the other way around in the other equation. So you find that for large K, most of the time, one of the components of the other is small. And also, if using that argument, if you sort of come back a minute, just a minute, if you use that sort of information, go back one. Sorry, something went screwed here. If this that UV is small, and if you subtract these equations, you get something reasonable. You'll get U minus V dot minus Laplace and then U minus dV, and plus FU minus GV. But you'll turn out the function U minus V, if you subtract UV is small, it means that U and V are close to the positive and negative parts of a function W. So what it means is, and we come to times, that's where it's that U minus V tends to be near a function W, and you get this sort of, Z, you get this sort of limiting equation. It's this limiting equation comes out, and this is hands waving you, but you can make it rigorous, that if K is large, UV is small, and U minus V turns out to satisfy good equations. Now this U minus V exists in the limit, satisfies equations with no large K term at all. So what you're saying that this is something I somehow dropped the page of. It means some of the limiting equations, you get these limiting equations which are quite good. And I made a comment that where D equals 1 matters. If D equals 1, life's a lot simpler, and you can see in this equation that Z plus minus Z minus just becomes Z. So the first two terms here are Z dot equals Laplacian of Z, which is a heat operator with some other perturbations. So if D equals 1, things are much simpler. And you can actually do more easily do things with it. So okay, so now come back. And that is in fact that difference why we can do things. Coming back on this is the first one. It's back one, sorry, my fault. And then it's just for that reason that if D equals 1, we get simpler equations which are much easier to work with, simply because if you look at these two equations and subtract, you get the first two terms are exactly a heat operator, while if D does not equal 1, it's much more complicated. And it's exactly a heat operator, which has much better regularity properties, is why the old paper worked. And that's why that came in. Now, and these, by the way, these then in another place, the estimates are easy. But in this case, the heat operator, in this more general case, it's a nonlinear heat operator with the regularity is much less well understood. And that's why we have more conditions here. Now, go on. Now the point being, and there's another difference in the proofs where it's very different. In the first theorem, we can actually, using what I was saying, we can estimate mod u dot and v dot, both in their bounds. They can estimate their supremum. In the first problem, you can estimate their supremum, which is a very good bound. And that makes the proofs much easier. In the second theorem, the problem is we can only estimate the L1 estimate, means the estimate for the integral of this mod absolute value of u dot plus the absolute value of v dot. You estimate the integral of that, and you can show that small near u equals v equals 0, which is much weaker than the other one. And you use, that's where it turns out in doing that estimate, you need two things. You need that tubular neighborhood I said before, and we must also need to estimate what the first eigenfunction of the Laplacian looks like on that neighborhood, because it really looks almost like something that's one-dimensional. But both of those are crucial to our argument, and that's why this estimate is much more thing. The other thing we need to use the span of the eigenfunctions of minus Laplacians in various spaces give you the whole space in some sense. And that is also important in the argument. In fact, it's crucial. And I'll come back to that in a moment. Now, what we remember in both the proof of theorems 1 and theorem 2, if we subtract the two equations, the k terms vanish and you get this set of equations where u dot minus v dot is Laplacian u minus dv plus f of u minus gv. And then if you differentiate in time again, we get this set of equations. This is rather trivial mathematics, where u double dot means the second partial derivative in time. So it's just a simple calculation. And you also get the boundary conditions as well. Now it turns out it's this we try and get contradictions if we had bad solutions. What we do is pass to the limit in this equation. Now this is technical, I'm not going to say much. Firstly, what we use the usual tricks. We integrate by parts, multiply it by a smooth function, integrate by parts, and put all the derivatives we can on the test function for, say, psi. And we multiply this by psi and integrate by parts, and it's put as many derivatives as we possibly can on the psi, and then you can. But then if we do that, we see that all the things only involve u dots and no space derivatives. So we've got a chance of passing to the limit, particularly since we've got quite good estimates for u dot and v dot. And we can actually show that u dot and v dot converge away from the bad set. And so we can pass to the limit in this, which I'm not going to write down because it's a mess. But it's crucial in this to be able to estimate u dot and v dot near u equals v equals 0. Notice that's trivial in the case where d equals 1, because you can bound u dot and v dot, so the control is easy. But anyhow, you pass to the limit. How are we going for time? Yeah. Okay. Then that's okay. And then what we passed, next on the page. I think that's the last page. Yeah, that's right. Yeah. Then the point is, we know, in fact, we can show when we're passing to the limit, u gets close to this, so the positive part of phi, the function we had at the start, and v gets passed close to the negative part of phi. And so we can actually pass to the limit in this in a weak sense very well. And the weak limit thing, which I'm not going to write down because it's a mess, but it's something that the set of eigenfunctions of the Laplacian, or its slight modification, linear combinations of them, infinite linear combinations gives all functions in the space. It's a completeness result. Say in space L2, we use that to show that we get a nice limit function. There's the point here. We know what U goes to and we know what V goes to, so we can show we actually get a good differential operator, which we can apply completeness theorems to, and we eventually get. We can actually show that we prove it for nice eigenfunctions, and then use that the linear combinations of those is the whole space. We can show we compress to the limit here, and using it once again the linear combinations of eigenfunctions gives the whole space. We can show we get we tend to get a contradiction unless the things are approaching the right limit. It's the last bit's rather not hard, but the tedious part of the proof, as you might guess. That's why I'm hand waving just a little bit, but you can make it work. It's very tedious, and and as I said, you've got to change it a bit if you have solutions with U and V are small, because the equations are a little different. But you've got to do a couple. You've got to do 2 or 3 three really cases. But this is the key case, and but you get fairly standard equations coming out. Yeah, there's some which you can handle, but it's messy, so I don't want to write all the rest down. But that's the idea. We can pass to the limit and get an equation that we can understand, but that's why it's crucial. We can already first prove that the solutions we're interested start like relatively close to a stationary solution, and that means we know roughly what they look like to the function U and V, and that's crucial to make the argument work. And that's how we actually get around a key problem. And just one other comment I should make is that you do know that if you ask what happens for general domains, you look at the stationary solutions, the stationary problem, I assume some conditions on those. One thing you do know is for most domains, the solutions of this are quite good. For most domains, the solutions indeed lie on C1 manifolds. That's what you might call the generic theorem. So it's those conditions we assume are true for most domains. Now, I'm not trying to pretend this is the final theorem one should aim for. It's got too many technical assumptions, which one would like to weaken, but it's certainly a start, because no one has made any progress on this problem for 20 years till now. And I might point out, it's a tedious thing to write out too. And that's a good place to stop, I think.
Awesome. Thanks very much, Norm. Any questions? Any questions?
Yeah.
Come on, there's no such thing as a stupid question. Just to prove that, let me ask a stupid question, Norm.
Yeah.
So what are some simple examples of physical systems with which these ODEs describe?
Well, this one is actually, this one is where you take something like foxes and rabbits in a region, and they would interact fairly strongly. And you're interested in how U might be the population of foxes. Yeah, right. It might depend on space. It might depend on which point in the space you are. And V might be the. No, say U might be the popular. Let's check this. Sorry, competing species. It's say two animals that both eat foliage. Say you might have a deer and a moose or something, and they are both competing in the sense they're both competing for the same vegetation. So the competition is on getting food to eat, and there's a lot of cases in biology where two species are competing for food supplies, and they also, if you've got two things competing for the same food supply, if one of them gets too populous, it tends to decrease the food supply for the other one and decreases its population. So it's really you get two species competing, and really you're trying to eat a very same or very similar food supply. Yeah, I think
And what's the simplest way to relate your, major results to that physical situation?
well, what we're asking, we're asking you, does the solutions over a long period of time, do they settle down to a reasonably steady state? Where in the sense,
Yeah, but how is that reflected in the, in the two competing species? As in, I guess, yeah, so you're just saying are they equally?
You're saying the populations of the two species, you're hoping to get the population of the two species stay reasonably constant in time, and they still might have a spatial distribution, but both species settle down to something that doesn't depend on time, but it may depend on space. Right. It's an equilibrium between the species.
Yeah.
Norm, just given that these solutions are talking about populations, is there any technical distinction between solutions that are compactly supported in omega or ones that have this spatial distribution running right up to the boundary and then vanishing under these boundary conditions? Can they vanish completely inside the boundaries?
No, they can't vanish They can't vanish on biggish solid pieces inside, because they can vanish on curves, but they can't vanish on solid pieces inside, because you can use the theory of linear equations to stop that. Remember, if they're U equals V equals 0 on the boundary, if they vanished on a sizable piece inside, then you could prove the solution of one component vanished on a piece, say, of positive area inside, then theorems say the whole solution must vanish everywhere. Does that answer your question? So it can only vanish on relatively small pieces. Now, small pieces, in fact, pieces of 0 area.
For this one, they cannot vanish at all, except on the boundary. These are non-negative solutions.
But they could. They possibly could be 0. Maybe I think I'd have to think about.
No, not for this one.
I
for the limiting problem. Yes.
Yes. Actually, Yihong's right. I think you can prove they can't vanish. They can't vanish in the interior.
Yeah. Just trying to find the limiting nonlinear problem. The Z equation. Just kind of find it. Maybe before.
I mean, it's interesting that they have this property. There's nothing analogous then to the maximum principle. This is a very naive question, because my knowledge of the Laplace operator is pretty elementary. But are you able to get any sort of analog of the maximum principle for these?
In a sense, you use maximum principle arguments in proofs, but the nonlinear terms negate the effect of the maximum principle to some extent. The maximum principle shows, in fact, our solutions, if they're not, either they're trivial or they're positive on the whole domain, and that is a maximum principle argument. But that uses maximum principles, but maximum principles only tell you certain things. And you use maximum principles in many proofs very much, but maximum principles only tell you a certain amount. And that certainly they tell you, but not linear equations, they tend to tell you a lot. For nonlinear equations, they only give you a certain amount of information. And so we can prove that the solutions we've got, either U vanishes entirely on the domain, which is a case I've tended to ignore for here, or U is strictly positive on the domain. Those are the only possibilities. And that is really a maximum principle argument, in fact, to show that they're the only possibilities. And so maximum principles come in, but they are, for nonlinear equations, they tell you different things.
And just to make sure I've understood the basics of the two theorems that you stated at the outset, so you've got whole manifolds of solutions from these, so there's no uniqueness principle or
there's no uniqueness principle in general. There is a uniqueness principle if you specify the initial conditions, then the solution is uniquely determined in the future. But there's many initial conditions. But but what we're trying to do is trying to understand, in fact, where the initial values has little effect. We're trying to understand the solutions over as the time gets large. And what we're trying to prove, the solutions actually settle down as time gets large. Yeah, unless there's now some outside disturbance on the system, which of course is a completely different question. But we're trying to prove that these solutions, if you after a large time, basically settle down to in fact, to something that's independent of time. And that's what we're trying to prove. And in a sense, we use a great deal that limiting equation has an energy. Not there. See, these population models, there's seldom an energy to make arguments with. And how you often prove solutions tend to stationary solutions is use energy arguments. But these are not available here because there isn't a good energy.
Are the stationary limiting solutions non-unique as well? Or?
Oh yes, they're non-unique.
Yeah.
They're non-unique. They may well be a number of them. And in fact, even if there's some
these large K case, yes, there are many stationary solutions.
There are many stationary,
Yeah.
and even sometimes if you have a symmetric domain,
Yeah.
you can have an infinite number sometimes, because you can have if you have say a circular domain, you may have solutions that are not radially symmetric, and you get what's technically a different solution by rotating it around a bit. So there's quite a few possibilities here.
Yeah, I guess
So
for this large competition or large interaction problem, I think what we know is that we can have many positive stationary solutions, and then people wants to know when t goes to infinity, so the solution don't oscillate around different stationary solutions. And actually here it shows, well, it has to convert to just one stationary solution, but mathematically it's very difficult to prove here.
Yes, that's
without a Lyapunov function.
Yeah, see, a Lyapunov function is something that decreases in time.
Yeah.
And but here in these population models, they tend not to exist. And that's the problem.
Yeah.
In a lot of physical problems, the energy, you can prove the energy decreases. In these, it doesn't work.
Yeah.
I've got a question from Ting Ying in the chat.
Yeah.
Who asks, so what does large K represent in the two competing species?
Well, it means the two species are competing very solidly. The two populations are basically competing very strongly for their food supply. Yeah, that's basically.
Yeah, I think, basically people say K measures the strength of competition. The stronger the competition, the bigger the K. If there's no competition, K equals 0. Yeah.
Right. So for example, with the what were we talking? I've forgotten the species we were talking about. Let's say sheep and goats.
Yeah, that's
if they only eat the same strand of grass, then they would be strongly competing. On the other hand, if they both ate a wide spectrum of grass species and their intersection was relatively small, that would be a weakly competing.
And certainly be a weakly competing. But
situation.
sometimes even if the food supply is very good, even if they eat the same things, the competition is so serious.
That's right. It's good we can relate this to Armadale's type things.
Yeah, I never thought of that, strangely. Even when I was working here on population models.
And just a different question, Norm. So back to the theorems that Adam was asking about. So you're basically saying that the equilibrium solutions are, you're not just getting to equilibrium states, but you're also getting to sort of reasonably smooth equilibrium states. So you don't have, you know, a singularity in space somewhere. You know,
No, they're quite, for these problems, the limiting state is quite smooth. That's
that's
not
very
a problem.
interesting.
And
Is
the
that,
model-
would you a priori expect that, or is that a surprise?
Oh, no, in these models, you would expect that because of the sort of model. There's different sorts of models where it can happen. You can get more complicated things, but in this sort of model, you would expect them to be smooth.
Mm-hmm.
Yeah. Yeah, in a sense that they'd probably get less smooth if one of the nonlinearities was very peaked.
Right.
And then you'd probably have less. You'd probably have less smooth. I think.
Right. Any other questions? So, if not, you don't need to forever hold your peace. You can get in touch with Norm privately, but we might stop it there. So, Norm, I'm going to electronically thank you by hitting this. There we go. So thank you for such a really nice talk, and thank you for coming up to Armadale. So I'll stop recording.
It's always nice to, if you can hear, it's always